I have been asked to talk about my experience as a researcher and to express my views about the conditions which must be fulfilled for science to thrive and to develop successfully. I will mainly talk about blue sky research. This expression, blue sky research, refers to scientific investigations which are based on curiosity, and I will discuss the connection of this research with applied research, which deals with technological innovations. I will start by a few remarks about the relations between science and society, and I will then discuss the connection between blue sky research, between basic science and applied science, and I will show by taking several examples based on my own field of research, which is quantum physics, to show how fundamental research leads often in unexpected ways to the development of technologies which have changed our lives during the last century. Having established, I hope, that basic research is necessary in a modern society, I will describe the ingredients which, in my view, are required for this basic research to be successful. Science, as we all know, has played a very great role to improve the lives of men and women in the world, especially during the last century. The constant increase in life expectancy, the development of agriculture, which makes it now possible to feed a population which for a long time has increased exponentially. It was 1 billion at the beginning of the 20th century, 7 billion now, probably 9 billion in 2050. And to feed this population, tremendous improvements have been made in agriculture to develop fertilizers and so on. I can also quote the control of epidemics, the gigantic technological progresses in transportation, in communication, in the processing of information. And these are only a few examples which show how lives have been changed, affected, I think, largely in positive ways by the global advances of science in modern times. And yet there is a paradox. In spite of these successes, or maybe because of these successes, science is often seen with suspicion by the public and considered as a threat for the life of the common person. Many people believe that scientists constitute, in fact, a powerful lobby which conspires to push forward its special interests. Examples of this are plentiful, going from the controversies which have to do with the use of nuclear power plants, for instance, the discussions which concern global warming, on the other hand, or the exploitation of genetically modified organisms. I believe that the distrust about science and about the goals of science is largely due to a lack of understanding about what science is about, and more largely to a lack of scientific culture in the general population. As we all know, the scientific approach consists in establishing facts, discovering phenomena, describing new effects, and then trying to explain them by theories which lead to the prediction of new effects, and this expands in circles, wider and wider circles, our knowledge about nature, and gives us more and more means of investigation. In other words, science informs us objectively about the world. This is the goal of basic research. And through this knowledge, it gives us tools for action, and this is the domain of applied research. Basic research has no other agenda than answering questions which are raised by pure curiosity. Why is nature behaving in such or such way? And to answer this question, we have to observe and to experiment. Theories are judged according to only one criterion. Do they agree with what nature tells us through the results of these experiments and observation? From there, a scientific truth emerges. And this truth is objective, and of course it is independent of any special interest. And after that, after the scientific truth has been established, it becomes the role of society at large That is the role of the citizen, the role of the public or private businesses, and the role of the political leaders, which represent the citizen in democratic countries, to decide what to do with information which is delivered by basic research, which are the applications which need to be developed, and which are the ones which have to be forbidden or controlled. Besides the scientific truth, there is another truth, other factors. There is a legislator truth, there is ethical values, there is a general interest, there are economic possibilities, and sometimes ideological considerations. But in this process, which has to do with society, science is neutral. It is neither bad nor good. It merely provides information and enlarges the realm of possible actions. To distrust science and to decide not to support basic research because of this distrust amounts to playing the ostrich, which refuses to be informed by burying its head in the sand. It is not the way mankind has progressed in the past, and it is not the way it should go in the future to respond to the challenges lying ahead of us. Of course, what I have said so far is largely understood by the scientific community, and I don't think I have to convince you of that. It's kind of common knowledge, common sense. And I'm sure it's also understood by political deciders. However, basic blue sky research is threatened by another insidious danger in a time of fierce economical competition, which is plagued by economic crisis. Why, often ask politicians, should we give taxpayer money or the money of shareholders, which is somewhat different but basically the same philosophy, why should we give this money to blue sky scientists who pretend to satisfy merely their curiosity without promising any specific application, without promising any specific thing in return? Why not concentrate limited financial resources on more useful, short-term, goal-oriented projects? In other terms, basic research is often seen as a luxury which is not affordable in present circumstances. And the blue sky researcher is caught between the suspicion of a part of the general public which sees him as a kind of wizard trying to manipulate the society, and the funding agency on the other side, which view him as an uncontrollable spender of public money. I already explained that the manipulative wizard image is based on a profound misunderstanding of what science research is about. The irresponsible spender image is, of course, also wrong. Even if one considers that the ultimate finality of science is to be useful, that is to result in marketable technologies or help solving major problems facing mankind in the domains, for instance, of health, energy, or environment, basic research must be supported because it is a necessary background upon which all applied technologies will grow and answers to the problems will be solved. I would like to illustrate this point, to achieve this, I will consider the development of my own domain of research, quantum physics, and I will remind ourselves of the way basic blue sky advances have led, often in unexpected ways, to the development of wonderful technologies. At the end of the 19th century, almost nothing was known about the microscopic world. Classical physics was successful at explaining macroscopic phenomena, the phenomena of our everyday lives, the laws of mechanics, the laws of electromagnetism, thermodynamics, but the atom and the photon were unknown, not to mention all the other subatomic particles. From the observation of some strange phenomena which did not fit in the classical picture, physicists, among whom most notably people like Planck, Einstein, and Niels Bohr, were the pioneers of the quantum revolution, which has revealed to us the strange microscopic world of atoms, molecules, and photons, and which has given us the knowledge required to develop modern technologies. One can say that these people lifted the veil which was hiding from us the microscopic world. The notion of photon, which are discrete particles of light, was introduced for the first time by Einstein in one of the papers he wrote during the miraculous year of 1905, along with the other paper on relativity and the paper on Brownian motion. And so he introduced the photon in physics. And 8 years later, in 1913, Niels Bohr invented his model of the atom, which applied for the first time the concept of quanta to the description of matter. I think it's appropriate to recall Niels Bohr's contribution because it's a beautiful piece of blue sky research, and because we are celebrating this year the 100th anniversary of Bohr's atom, which is considered by many as the 100th anniversary of quantum physics. In fact, Bohr's work intended to explain an experimental fact, to explain the spectral properties of atoms. You see here a spectrum of atoms which show dark lines and bright lines. In fact, it wanted to explain why matter was emitting or absorbing radiation at discrete wavelengths. This had been observed through the observations which had been made possible in the 19th century by the great improvement of optical instruments. So it was a question of pure curiosity. Why is matter emitting or absorbing radiation at discrete wavelengths? And this has led him to realize that this discreteness in the spectrum implied that the radii of electron orbits around the atomic nucleus should also take discrete values and thus be quantized. And so he introduced the notion of quanta for the first time in the description of matter. Bohr did not anticipate that useful applications would proceed from the answer to what was a curiosity-driven question, and it did not even consider at that time this possibility. A few years later, de Broglie introduced the idea that if light is at the same time a wave and a bunch of discrete photons, as Einstein has said in 1905, then material particles such as the electron, which are classically seen as discrete entities, must also have a wave character. The dualism between wave and particle aspects of matter and light was finally explained by the complete, full-fledged quantum theory, which was developed mathematically by people like Heisenberg, Schrödinger, and Dirac in 1926. This theory disclosed to us a world in which the superposition principle is ubiquitous. This principle tells us that particles, and more generally quantum systems, can be in different states at the same time, so to speak, suspended between different classical realities. This is a very strange word indeed for classical mind, and trying to understand it has led the builders of the theory, the founding fathers of the theory, into passionate debates. I will say more about this aspect of the story in my next talk, which will be more specialized in quantum physics. There is no doubt that all this story from 1900 to 1930 belongs to the domain of pure blue sky research. The scientists were at that time motivated solely by the desire of understanding nature. Their approach was exactly the one I defined at the beginning of this talk, observing phenomena, then trying to explain them by theory, which in turn led to the prediction of new effects whose subsequent observation either vindicated the theory or disproved it, and then they had to proceed by this try and error approach. It is true that some of them had the premonition that what they found could lead to applications, for instance, concerning the possible use of nuclear energy. But this was not what was driving them in the first place, and they certainly did not try to justify their work by utilitarian arguments. Almost a century later, it is instructive to reflect upon the breadth of what this blue sky research in quantum physics has produced in our knowledge about nature. From the infinitely small to the infinitely big, covering over 60 spatial or energy orders of magnitude, quantum theory is used as much to describe the still largely mysterious vibrations of the microscopic strings that could be the basic constituents of the universe, as to explain the fluctuations of the microwave radiation which is reaching us from the depths of the outer space and which can be represented in false color in these big maps of the sky which are produced by satellites that you can see on the right. And between these two extremes, you can find all the objects of the world around us. If you add 20 zeros to the dimension of these hypothetical strings, you have the size of an atomic nucleus, 10⁻15 meters. And it is the heart of, as you know, of radioactivity and nuclear energy. If you add 5 zeros next, you reach the size of the atom, where you have a nucleus held to its cortege of electrons by the electromagnetic force. And you can explain in this way also simple molecules, which are small clusters of atoms which form and break according to the laws of chemistry. And chemistry is also an upspring of quantum physics. If you go another 2 or 3 orders of magnitude, you reach the size of biomolecules, where life manifests itself at the most basic level. And to understand the connection and the bounds between the atoms in this molecule, you need, of course, to have quantum laws. If you add still another 6 to 9 orders of magnitude, you find the range of dimensions going from 1 centimeter to a few meters. That is the human scale, with its diversity of solid, liquids, gaseous objects, whose understanding also is based on quantum physics. From that scale to that of astronomical objects, planets and stars governed by gravitational force, you have to add 8 or 9 zeros, and finally, with another 16 orders of magnitude, you complete the journey and you get to the universe as a whole. And everybody knows now that the cosmologists need quantum physics to understand how the universe started something like 14 billion years ago. So along this vertiginous journey we have just taken, physics must describe and explain an infinite variety of phenomena. Some of these phenomena, of course, have been known for a long time, like why the blue color of the sky, because since I named this blue sky research, why is the sky blue? This is one phenomenon. Others phenomena have been discovered during the last century owing to the development of powerful means of investigation. And at the far ends of the infinitely small and the infinitely big, you still have problems which raise questions which remain unsolved, and that's why we build accelerators like the CERN or big telescopes like the ESO telescopes, which is now being built in Chile. But few of these phenomena have not had at least some aspects which have been brought to light by quantum theory, which has accomplished brilliant achievements over the last century. The theorists will no doubt point to the extremely precise description that quantum physics provides of the interaction between electrons and photons in quantum electrodynamics. And this is a topic that I will approach and describe more in my second talk. The theorists will also note the remarkable quantitative agreement between experiment and theory. They will also talk about the unification of 3 of the 4 fundamental forces of nature, the electromagnetism, the weak and the strong nuclear forces, making up what we now call the standard model of physics. And they will also mention the promising attempts to include gravitation into this unification by developing a quantum string theory. And they will finally insist on the universality of physics, which is a remarkable consequence of the properties of quantum theory. The theory explains the spectrum of the radiation emitted by the hydrogen in the discharge lamps in our laboratories, but it also describes the properties of hydrogen in outer space, and the light and the electromagnetic radiation of this hydrogen atom are received by radio telescopes after having traveled billions of years through space, and we understand them because we understand how hydrogen behaves in the lab. Quantum chemistry applies to the reaction in a chemist's test tube, as well as to those that take place in the specks of intergalactic dust, in which molecules are formed and separated, and their radiation is picked up by our telescopes after millions of years traveling through space. Finally, cosmology and the parallels it allows us to build between the infinitely small and the infinitely big, which is stimulated by quantum theory, highlights the profound similarities between the phenomena which occurred at the origin of the universe in an environment whose density and heat are impossible to imagine, and those that occur during the violent collisions between particles in our giant accelerators. So this fundamental knowledge, which is once again the result of basic blue sky research, has led to many wonderful applications to technology. Because it provides us with in-depth knowledge about the phenomena that take place within matter, quantum physics offers us means of action, of computation, and of diagnosis of a power and precision that were previously unimaginable. Take the small laptop which is used in the present lecture. If you examine the insides of this laptop, you would find a small case under the keyboard which contains a silicon chip which is just a few centimeters long. And on this chip, you will find a labyrinth of electric circuits printed. These circuits link stacks of semiconductor materials, tiny transistors, which constitute as many small logic gates. The properties of these materials are governed by quantum laws. One talks about the tunnel effect, about the Pauli exclusion principle, and other quantum phenomena. Articulating these laws make it possible to perform highly complex programmable computations, as you know. The principles of a computer have been known for a long time. In fact, the capacity to store information and to compute in material systems goes back at least as far as the Pascal's machine that you can see on the top of this slide, which was imagined by Pascal and built by Pascal in 1650. The principle of computing programming is attributable to Babbage, that you can see on the right, who in the 19th century imagined a complex machine which is made up of an assemblage of cogs and mechanical elements. In the 20th century, the development of the electric industry led to the replacement of these mechanical circuits with vacuum tubes, and thus the first computer of the modern era. The early machines that were developed in the United States before and just after the Second World War, like the ENIAC machines that you can see here, were nevertheless enormous and largely unreliable, and they required constant maintenance by an army of technicians, and their performance was far inferior to that of the small modern computer that you see at the bottom. The discovery of transistors and the possibility of integrating huge numbers of them into a semiconductor material is what allowed for the proliferation of computer applications. The logical principle of the computer could have been understood by a person of the 19th century, but its practical realization necessitated technology that would have been impossible to conceive in a pre-quantum world. The laser is another example of an invention which is based on the quantum effect and which is now omnipresent in our daily lives. When I was a young student, I remember how I marveled at the first lasers which were emitting their directional beams of intense and monochromatic light. Nowadays, this is no longer a remarkable sight. But until the 1960s, nobody had ever seen anything like it. Since the origin of mankind, light had been a rebellious wave which was awkward to direct and to concentrate. And the oscillation of the electromagnetic field which makes up the light have been difficult to control. The laser changed this and allowed us to domesticate radiation, and it did that by exploiting the properties of atom-stimulated emission, which were established by Einstein in the early days of quantum theory. Lasers now have an infinite number of uses, from the most trivial to the most sophisticated, from the reproduction of sounds and images recorded on compact discs to the barcode readers of supermarket checkouts, through microsurgery or fiber optics telecommunication. Another important application of quantum physics relates to the precise measurement of time. The atoms in each element emit and absorb light at characteristic, unchanging, and well-defined frequencies. As a result of this fundamental quantum property, the measurement of time is now no longer based on the oscillations of pendulums, of springs, or quartz crystals, which are subject to perturbations, or even on the movement of stars and planets, which also fluctuate despite their apparent regularity. Instead, the measurement of time is founded on the oscillations of physical variables associated with atomic electrons in atoms. Thus were born the first clocks that now define time with a precision of the order of a second over geological eras. These are atomic clocks, and when you synchronize them together and you send them on board of satellites and send signals to the receiving devices of the global positioning system of the GPS, you get a fantastic device. By measuring the instance of arrival of these signals, the position of the receptors can be determined by triangulation with an ultimate precision of a few centimeters. These devices have, as we all know, become standard navigation tools, and no one is surprised anymore to be directed in this way from the sky with an extraordinary precision. I will take as the last example medical magnetic resonance imaging, MRI. It's a technology which is based on the understanding of quantum processes too. The MRI images are actually produced by the convergence of three quantum technologies developed to a remarkable level of sophistication. A powerful magnetic field, which is produced by superconducting coils, and superconductivity is a quantum effect, is necessary, and then sequences of radiofrequency fields which are suitably arranged create resonance between the magnetic moments of the nuclei in our atoms, and this magnetic resonance effect is another effect that only quantum physics can explain. And then the signals emitted by these nuclei are finally processed and transformed into images by powerful computers, which are constituted of materials within which quantum effects, as I have said, also play a powerful role. We can thus, for example, reconstitute the inside of our brain in 3 dimensions, and we can even follow the evolution of the cerebral activity that modifies the signals emitted by our protons. The thought, or at least its material manifestation, thereby becomes visible. When the scientists developed magnetic resonance in 1946, Felix Bloch and Ed Purcell, they developed it as a blue sky research experiment, and no one would have imagined and even dreamed about MRI, of course. So what do all these inventions, which are founded on the understanding of microscopic phenomena, share in common? Originally, the study of these phenomena was not driven by the application it would come to serve at the end of an often fortuitous journey. What stimulates research is first and foremost curiosity for its own sake, the need to understand the intimate nature of things. Applications only come later, and often where we did not expect them to occur. When the first laser appeared in 1960, no one knew what purpose it would serve. Back then, we called it, only as a half-joke, a solution looking for a problem. Neither the laser, nor the laptop, nor the MRI could have resulted from an utilitarian program. In fact, and now I will try to make some comparison between blue sky and applied research. In fact, there is often no sharp boundary between the two. In the examples I have taken, it is sometimes hard to tell when the investigations are no longer driven by mere curiosity, but become goal-oriented. In the case of the laser, for instance, it is clear that its discovery was blue sky research. The inventors realized that it was possible, by using the principle of quantum physics, to build a new source of light with properties radically different from that of classical lamps, and they decided to take the challenge to build such devices with no other specific goals in mind than just to meet a challenge. Once the laser was there, it became clear that by improving on various characteristics of the laser light, interesting applications would become possible, and the task of developing this application involved the parallel work of physicists working to understand fundamental questions and engineers trying to solve technical issues and turn lasers into practically usable devices. One way to distinguish operationally between blue sky and applied research is to analyze how these two forms of research are practically carried out. Basic research cannot be programmed in details ahead of time, since, by definition, one does not know what will be found. This is the definition of research. Freedom must be left to the scientists to define their own program and to change it as the research develops, taking into account what they have found in the way. Applied research, on the other hand, wants to meet specific goals assigned ahead of time. Its natural management thus involves a lot of programming. It has to define milestones, steps which has to be achieved in the way, and this must be achieved in a well-defined timetable. And it generally works towards the production of a deliverable device useful for a specific task, generally marketable for a profit. A mistake which is often made in the organization of research is not to recognize properly the frontier between blue sky and applied research, and to apply to research a wrong form of management. Let me illustrate this by two examples. When the USA decided to build a nuclear bomb during the Second World War, it developed a successful program of applied research called the Manhattan Project. The blue sky research on nuclear fission performed during the years preceding the war, notably by Otto Hahn and Lisa Meitner in Germany, and theoretically by Niels Bohr in Denmark, Otto Fritsch in England, and Wheeler in the USA, had basically solved the theoretical problems and shown the way to build a fission bomb. The rest could be carried on according to an applied project with well-defined milestones, provided enough resources and money were gathered in order to solve the technical problems on the way, such as isotope separation, for instance. And so it was a successful project. And again, I am not judging whether it was good or bad. Science gave a possibility, and then the society decided, and the governments in the situation they were in during the war decided to go forward. 30 years later, the Nixon administration in the USA decided to apply the same strategy to the fight against cancer, viewing it as a kind of Manhattan Project in medicine. In spite of the important resources which have been put in it, it was largely a failure because the procedure adopted to an applied project were developed to deal with a problem which belonged largely to the domain of blue sky research and not applied research. One did not know enough about the mechanism of this multiform disease to consider the task of curing it as being merely a technical issue. Since then, impressive advances in cancer therapy have been made, but through blue sky and unpredictable advances, impossible to predict and to program ahead of time in a kind of Manhattan Project. So what are the ingredients for a successful blue sky research? The scientist must be given two riches which are absolutely necessary: time and trust. Time, because it is very challenging to discover new things about nature. It is a long process with a lot of pitfalls, wrong avenues, and mistakes to be made in the way. Trust, because a successful research should be able to overcome inevitable drawbacks. The scientists must feel that they will be supported in spite of possible errors and judged by their peers only at the process. The difficulty, of course, for the managers of science is to decide who should be trusted and who should be given time. One good indicator is past achievements. There is a high probability that a scientist who has been successful and productive in the past will keep being productive in the future. The trust factor is, of course, more difficult to define for young scientists who have not yet achieved anything. Who will become a great scientist and who will fail is hard to assess. There, it is largely a matter of intuition. The good laboratory directors are the ones who are able to see far ahead the promises of young investigators and decide to trust them to achieve their goals. Time and trust are, of course, two notions which are alien to applied research projects. There, scientists are asked to deliver under time constraints, and the principle of trust is replaced by the notion of contract. The scientist must sign that he or she will be successful within well-defined time and with well-defined money limits. And once again, this can work only if the problems lying ahead are merely technical and all the fundamental issues have already been solved. Unfortunately, though, the tendency now in research throughout the world is to apply to all forms of research the same management, copied on the applied research model, and to neglect the time and trust requirement. This has not always been the case. When I started my own research in France in the 1970s, I worked under the time and trust system. I did not have to write frequent proposals. I could develop my research at my own pace until the protection of a lab director, Jean Brossel, who had a gift for recognizing promising young scientists. This laboratory, which is now called the Kastler-Brossel Lab, is still trying to work according to the time and trust principle. Also, it becomes more and more difficult to do with the boundary conditions which are imposed by new ways science is managed. The success of this way of doing research is attested by the 3 Nobel Prizes which have been awarded to its scientists. You see on this picture, which was taken in 1966 in the lab, Kastler-Brossel, on the day the Nobel Prize of Alfred Kastler was announced. I was then a graduate student that you can see on the right and unfortunately not recognized, so you give the names below. Next. So I was a young student there, and my thesis advisor, Cohen Tanucci, who is also in this picture, was to receive the Nobel Prize in 1997, 31 years later. So you see that this was successful, and this kind of blue sky research management gave good results. In contrast, in the USA, project-oriented programs have since long ago been the general rule. University professors, as well as young assistant professors, had to apply for research money through short-term grants to the NSF or to the NIH. A notable exception to this rule were the Bell laboratories. The Bell Labs are laboratories which thrived from the 1930s to the 1980s, and there the time and trust principles were fully applied. The lab directors, after having carefully selected their scientists, let them free to work on what interested them without having to spend time on writing proposals. The result was at least 7 Nobel Prizes for discoveries as diverse as the wave nature of matter, the transistor, the cosmological background, the laser cooling of atoms, or the digital camera. In the 1980s, however, when the Reagan-Thatcher neoliberalism developed without constraints, the Bell Lab disappeared, at least in the very fruitful and productive form. When the Bell company, renamed AT&T, lost the monopoly of telecom in the US, it had to compete with other companies, and its shareholders found it counterproductive to support blue sky research without control. The law of the market was ruled by the notion of short-term contracts, which had to apply to all researchers. At that time, the same evolution started in Europe and in France, and the research, which used to be largely supported by institutions in which the time and trust policy was possible, became more and more dependent on contracts. I was by then well established as a scientist, and I was able to get the contracts I needed. But I think that this situation was bad, and still is bad for young investigators who have to spend more and more of their creativity time writing proposals and being constantly evaluated. I am worried by this evolution. Immediately after being awarded the Nobel Prize, I was asked to write an editorial piece in Nature, and I decided to stress in it this point. The passion for blue sky research has to be nurtured in young scientists who should not be handicapped by bureaucratic tasks and should be paid decently in order to have the freedom of mind to develop their creativity. Let me end by a last remark. Blue sky scientists are stressing now more and more that what they do will be one day useful for society. And they do that much more than what people like Bohr or Einstein did at their time. Is it true that mankind is facing now formidable challenges which can be solved only by scientific advances? But this is not the only reason for this evolution. After all, challenges of another nature did exist too at the time of Einstein and Bohr's seminal discoveries. Another motivation for emphasizing the usefulness of blue sky research, as I am doing now, is that basic research costs more and more in a time when money becomes scarce. If Röntgen or Otto Hahn discoveries of the X-rays or uranium fission were made with very simple tabletop apparatuses which did not cost much. A few weeks ago, I visited the Deutsches Museum in Munich, and I have been amazed at the simplicity of the setups which are displayed there, which they used for this discovery. At that time, the money spent on equipment was probably not more than the paycheck of the professor doing the experiment, and things have changed a lot since then. Now, experiments, even tabletop ones, cost much more. Emphasizing the usefulness of basic research is a way of saying to the politicians, and through them to the taxpayers, that their euros or their dollars or their pesos spent on blue sky research are not given to fulfill merely curiosity, but will serve long-term goals. The difficulty of this discourse is double. First, we do not know what these goals will be, since, as I have shown above, the path from blue sky research to application is largely unpredictable. Past experience tells us that good basic research will most probably lead to innovations, but it also tells us that it will take a long time and that we don't know what will come out. In fact, I am always facing this when I am asked what is the usefulness of what you are doing, and we'll talk about that in my next lecture. And so this is, of course, a big problem. And there comes the other difficulty. Money spent today will directly serve society in 10, 20, maybe 50 years from now. And this is not easy to swallow by taxpayers who have economic problems now, and by politicians who are looking at their short-term political agenda with the horizon of elections coming a couple of years ahead. So we are again confronted with the issue of time. The time scale of science is not the same as the political time scale of democratic societies. And adapting these two disparate timescales is a formidable challenge they have to face if they want to solve long-term problems such as the global warming or the energetic transition. So I think it's a big problem when you deal with science and society. It's also a big problem when you deal with education. Everybody will agree that if you educate well young children now, it will make a better society in 20 or 30 years from now. But people cannot do that because they cannot really project themselves in 20 or 30 years. And again, it's a matter of discrepancy between the time scale of the problems to solve and the time scale of politics. So this is a little bit discouraging, but I would like to conclude on a more positive note. Attempting to justify blue sky research by its utilitarian side only is not the full story. It reduces it to its economical aspect. But science, and especially basic science, has another dimension. It is a priceless aspiration of mankind, I believe, at the same level as art. Science satisfies the need for rational understanding in the same way as art tries to satisfy the need for beauty. These are priceless concepts, and I think in a time of economical problems, it is very important to understand that there are other things which cannot be measured in terms of money that mankind is interested in. So I would like to say that even if it were proven that some form of blue sky research will never have any application, and this is of course impossible to prove, you cannot prove that something will never happen, it should nevertheless be pursued just for the sake of it, to satisfy a basic need of mankind which cannot be evaluated in terms of dollars. So next slide. At the two ends of the energy scale I mentioned at the beginning of my talk, let us consider the research carried on to understand the physics of the infinitely small with gigantic accelerators such as the CERN one, or the mysteries of the infinitely large with huge telescopes such as the ones built across your border with Chile. These pursuits belong to this kind of priceless research. It is hard to tell which will be the use of the Higgs boson, for instance, or that of the dark matter, even if the technologies which are developed to build these accelerators and telescopes have already found their use. An example of indirect application of high-energy particle physics is the Internet, which has evolved from the work of CERN scientists trying to find ways to communicate between them via computers in the early 1990s. Such applications are, however, clearly not the motivation of this kind of research, which is driven by pure curiosity, trying to answer the eternal questions. Where are we coming from? Who are we? Where are we heading to? These questions are symbolically expressed in the famous painting by Gauguin, which bears this strange and mysterious name. He wrote this name at the bottom of his painting in the form of a fundamental question mark. It is comforting to realize that mankind is still able to pursue this kind of very expensive quest without asking for any direct material reward. And I thought it was appropriate to conclude this talk by making this, I must admit, a little bit far-fetched connection between science and art. Gracias.